grateful to the organizers for inviting me here, because I don't really do understand localization. I do normal sort of spectral theory. I haven't yet mastered probability, so please forgive me. But I think it's somewhat related, you know, to what you guys do. So what's a typical problem in my subject area? So here is a typical problem. We have a resonator, a domain in R3, and we study the eigenvalue problem, minus Laplacian V equals lambda V, say with the Dirichlet boundary conditions. And we want to find the eigenvalues. Now, finding the eigenvalues is difficult, so we introduce a counting function, number of eigenvalues below a given lambda. And we study the asymptotic behavior of the counting function as lambda tends to plus infinity. And it's known that this counting function admits an asymptotic expansion. Here it is. So the number of eigenvalues below a given lambda grows as lambda to the power 1.5, and the coefficient is proportional to the volume of the resonator. This is yes, I've read both papers. Now, you see, the way you as a physicist know Rayleigh genes is this formula plus a physical interpretation. So you have to differentiate this formula, which you cannot really do for a non-smooth function. But you say there are so many energy levels in a given interval, and then relate it somehow to the radiation of a black, absolutely black body. I do not understand the second bit. I read the papers of Rayleigh and genes, and this is what it is. Now, how did Rayleigh derive this formula? Okay, maybe.
All right.
Maybe.
It has only.
No, it's an interesting question. Rayleigh considered the cube, calculated the eigenvalues, and wrote this formula and says, of course, if it works for a cube, it will work for any other shape.
Correct.
It is correct, yes. But why did it take 2 Nobel laureates to write down such a simple formula? Because Rayleigh made a mistake. He wrote the coefficient incorrectly, had an extra factor of 8 here. And Jeans replied by publishing a paper of 1 sentence. It seems to me that Lord Rayleigh put an extra factor of 8. And Rayleigh replied by saying yes. So this way it became the Rayleigh-Jeans law. Now, as usual, all the glory went to the physicists, and nobody noticed Hermann Weyl proving this result in 1912 for an arbitrary resonator. Now, Hermann Weyl, he went further. He conjectured that one can do better, that one can write a two-term asymptotic formula, where the second coefficient would take account of boundary effects. So the area, surface area of the boundary should appear in the second asymptotic coefficient. And proving this was much more difficult. The proof was given under certain geometric conditions by Victor Ivry in 1980.
It's only for the Dirichlet boundary condition.
To add the next term, which is James.
You see, there are a number of theoretical difficulties. You cannot do it with a counting function. You can mollify the counting function. You can, take a convolution with the Schwarz class function. Then you can do it. But for the counting function itself, you cannot do it. There are a number of theoretic obstacles.
But this is only for Dirichlet boundary condition.
Pardon?
This is only for Dirichlet boundary condition.
For Neumann, you get a plus.
For some other, you have some other.
Yes. So that 1980 was the time when I was starting doing research. I couldn't prove the Weyl conjecture, A, because I couldn't prove it, and B, because Ivry did it. So I had to do something. So I obtained similar results for higher order operators. And that's this way I built my career, on this result. This resulted in a book, which we published eventually with Safarov. And I cannot resist to advertise the book a little bit, so some kind words from the reviewer. Now, how are these results obtained? The modern way of deriving spectral asymptotics with high accuracy is the following. You introduce time into your problem. Your problem did not have time, it had a spectral parameter lambda. But you introduce time, you consider a dynamical problem, you study a Cauchy problem for a propagating wave. So you now have time, you have initial conditions, you want to see how this thing propagates, and you introduce the concept of a propagator, so the operator which solves the Cauchy problem. Now, doesn't seem to help much, because how do you construct the propagator? However, there is an effective procedure for constructing the propagator if you are prepared to lose smooth contributions. There is a whole subject called microlocal analysis, was started by Levitan, Hermander, and they give you a recipe how to construct this propagator. The idea is pretty straightforward. You first thing, suppose my coefficients were constant, I know how to do the Fourier transform. I write everything explicitly. Then I remember, oh, my coefficients are variable, so I have to correct it. And there is a rigorous way of sort of doing this iterative process. It's somewhat similar to Feynman diagrams, only the difference is this is completely rigorous. There are 4 volumes of Hermander which you can read and learn this technique. It's possible to construct the propagator if you are prepared to lose smooth contributions. And knowing the propagator and some number theoretical Tauberian theorems, you can recover the asymptotics of the spectrum. Reading Hermander's book is pretty difficult, 4 volumes. This book, unfortunately, is also pretty difficult. I've been reading it lately, and I found it to be difficult as well. But anyway, this technology exists. Now, okay, we should write an even clearer book. Somebody should do it. But after we wrote this book, I thought that there's nothing interesting to be done in classical sort of spectral theory. No disrespect to those who continue doing it, but I lost interest. Until a couple of years ago, I realized that there is something fishy about publications on systems. So today I will consider a system. See, most of the publications were on scalar operators, and then people said the same works for systems. Now, today I will consider a first-order system. Usually spectral theorists start with a first-order system. It's sort of the basic case, and then try to reduce, an arbitrary order to first order. But let it be just first order. I do not want any boundary today. I don't want to struggle with boundary effects. I just work on a manifold, closed manifold. This analysis can be done with a boundary. I just don't want to bother with the boundary today. I've spent the best years of my life, struggling with the boundary effects. So on this manifold, I have a system. The manifold has dimension n, and I have an m by m matrix differential operator. Okay, maybe pseudo-differential, doesn't matter, differential for simplicity. And this operator is elliptic in the sense that the principal symbol doesn't vanish. The spectrum can go to plus infinity, minus infinity. I do not assume sign deafness. So of course I'm having the Dirac operator at the back of my mind. But I'm just considering a general self-adjoint elliptic system. The principal symbol, for those who don't know it, is just, you leave the higher order coefficients, derivatives, and replace each differentiation by I psi. Psi is the dual variable. A physicist would call it momentum. Microlocal analysts, for some reason, call it psi. So, I want to study the following objects. I want to study the counting function, number of eigenvalues between 0 and a positive lambda. I have to be slightly careful here because the spectrum may go to minus infinity as well. I better decide, whether I'm studying positive or negative. So today I'm studying positive eigenvalues. And I'm also studying a local version, something called the spectral function. Spectral function, it's like the counting function at a point. You take the Euclidean norm of the eigen functions, square them, and sum overall, lambda k between 0 and lambda. If you integrate, you get the counting function. So spectral theorists like sometimes working with the spectral function because it's a local version, more general sort of object. And I want to derive two-term asymptotic formulae, as everyone does in the subject area. And okay, so for the counting function, the spectral function, And of course, the coefficients here and here are related in an obvious way. You integrate this coefficient, you get this coefficient. So this is what I'm aiming to do. It was all done 32 years ago. Why am I doing it today? Because things are not as simple as they seem. So in one of the first publications of Ivry, he was dealing with the Weil conjecture. He published all these proofs and so on. And in the end, he used to say, the same works for a system, and gave a formula for the second asymptotic coefficient, which was incorrect. He wrote that the second asymptotic coefficient should be proportional to the subprincipal symbol. Okay, it doesn't matter what the subprincipal symbol is. He took sort of an analogy with the scalar pseudo-differential operators. The real formula turned out to be far more complicated, but he thought that it was proportional to the subprincipal symbol, the second asymptotic coefficient. Why did this happen? There was great excitement around Ivry's work. There were rumors that he was considered for the Fields Medal. I don't know whether it's true or not, but what's true, he was invited twice to give talks at the International Congress of Mathematicians. Twice the Soviet authorities didn't allow him to travel, but anyway, there was great excitement that he tried to announce as many results as possible. In '82, he realized that that formula was incorrect for systems. For scalar operators, there is no problem. And wrote a new formula. Still incorrect, still proportional to the subprincipal symbol. Roughly the same time, Rosenblum wrote down a formula also incorrect, also proportional to the subprincipal symbol. In '84, Ivry published a book in Springer Lecture Notes, where he wrote that all previous formulae for systems were incorrect, and he couldn't give a formula, he gave an algorithm. So the algorithm, okay, he knew by then that things are much more complicated for systems. You have to take some contour integrals, go to the limit and so on. If you succeed in understanding this algorithm, you will still end up with an enormous numbers of terms to calculate. Say for a system of two equations, it's 96 terms, and they're pretty difficult, each of these terms. Now, there is another book in '98 with the same algorithm carefully hidden, and there is one book coming out this year, I think 3,000 pages long. I think the algorithm will be there as well. However, in 1989, Yuri Safarov, my co-author and friend, he came up with an actual formula. It was his Doctor of Sciences thesis, in the Stiklov Mathematical Institute, and there was a formula. This formula was not the main result of the thesis. The main result was something else, but it was a nice formula, and okay, I read the thesis, I wrote a positive report, and I was happy. But then I started worrying a little bit, and I had a PhD student. I asked a PhD student to check Safarov's formula, and he couldn't check it in full, it's too complicated, but he managed to check the formula for the principal symbol of the propagator, which was already a massive task. So we knew up to which point things were done correctly. Then in 2007, there was a paper by Ruzhansky and Kamotsky, long paper, which ends with a theorem. There is a two-term asymptotic formula, but we don't give you the coefficients, which was a close call. It's good that they didn't give it. Anyway, 32 years, we don't have a formula until now. So this is a paper that will appear in Journal of Spectral Theory. So here is the formula. Now, as usual, you have to integrate over some sort of balls in the cotangent fiber. So this is standard structure, but you are integrating three terms. The first term is the obvious one, which involves the so-called subprincipal symbol, but the other two are not so obvious. You see what happens here. You have these eigenvectors of the principal symbol. Eigenvectors of the principal symbol arise because, okay, you think, suppose the coefficients are constant, I want to solve, find solutions as plane waves, I get, these plane waves, and the eigenvectors of the principal symbols appear as amplitudes. And then you have to start doing all sorts of operations with these eigenvectors of the principal symbol, using invariant constructions, like the Poisson bracket. You can do the Poisson bracket not only on scalar functions, you can do it on matrix functions. It still is an invariant object. So you get something else. Now the last term is written in red, because this is the term we had to add. These two were Safarov's term, and that's what was missing. So in the next 5 minutes, I'll discuss the geometric meaning of what was missing in this formula. And the geometric meaning, in my view, is beautiful. So what happens here is when you construct plane waves, when you look at eigenvectors of the principal symbol, you have a problem. You do not know how to choose it. There's always a gauge transformation. You see, you are looking at an eigenvector of a matrix. So in the complex setting, you can multiply it by e to the I phi. You don't know how to choose this phi. It's a gauge degree of freedom. It could be an arbitrary function. And when you have a gauge degree of freedom in physics, somehow in geometry, it leads to some serious consequences. You cannot just brush it totally under the carpet. So what happens is you say, oh, maybe I need to introduce a connection. And the natural way of introducing a connection is to parallel transport your eigenvectors of the principal symbol so that they remain orthogonal. The derivative remains orthogonal to the eigenvector itself. That's the only natural parallel transport law you can think of. And this, in plain sort of English, it means introducing an electromagnetic vector potential. So if you think about parallel transport of these eigenvectors of the principal symbol, you see that you have an electromagnetic vector potential given by an explicit formula. The only difference with the normal, electromagnetism is that everything happens on the cotangent bundle. In normal electromagnetism, everything happens on the original base manifold. And here you get a covector potential which lives on the cotangent bundle. But it's all explicit construction. And then you think, if I have, covariant derivative with this potential, covector potential, maybe I should form a curvature tensor. You get an analog of the Maxwell tensor, of the electromagnetic tensor, but living on the cotangent bundle. And then you think, maybe I should take a trace to get a scalar component. With the usual electromagnetic tensor, you cannot take the trace. Okay, you can, but you get 0. But here, because you have a separation between position variables and momentum, you can take the trace of this block and gives you, okay, that expression that was missing. Okay, the bottom line is that whenever you study a system with variable coefficients, there is an electromagnetic field, internal field, sitting there inside. It's a general fact, nothing to do with spectral theory. For some bizarre reason, it was never noticed by analysts working in the spectral theory, analysts working in partial differential equations. Okay, but now the real fun starts. I want to somehow handle the Dirac operator, massless Dirac. If you forgive me, I haven't yet mastered the massive case. So let's put some additional assumptions. Let the dimension be 3 of the manifold. Let the number of equations be 2. Okay, and let the principal symbol be trace-free. So the simplest possible situation. What happens in this special case? You get additional geometric structure. Initially, I didn't have any geometric structure. I just said, I consider, a first-order operator. But now we have an additional geometric structure. Firstly, you can take the determinant of the principal symbol. And you see it's a quadratic form in momentum, because it's a 2-by-2 matrix. So you say, I call these coefficients the metric. So you have a metric, first geometric object. Then you have a more interesting geometric object. You take a point on a manifold and take, it should be psi, and take a vector, covector psi based at this point. And now I want to parallel transport it to another point. How do I do it? I need a law for parallel transport. And here is the law. I want the principal symbols to be equal to, this principal symbol to be equal to this principal symbol. Gives you in dimension 3, it gives you exactly 3 real equations for 3 real unknowns, components of this C tilde. So you have a connection. And this connection, you can calculate the connection coefficients in terms of the principal symbol explicitly, but it has some interesting properties. It has 0 curvature. It doesn't depend on the way you parallel transport your co-vector, because you are just, here is the law, you know, there is no curve connecting these points, it just, it's irrelevant. So the connection you get, it's called the teleparallel connection, and it's the opposite of the Levi-Civita connection that most people know. So Levi-Civita connection has zero torsion, non-zero curvature. This one is the other way around. It has non-zero torsion, but zero curvature. That's the second geometric object. And the third geometric object I call topological charge. If you calculate this number, it can take only values plus and minus 1. So it shows the orientation of the principal symbol with relation to the chosen orientation of the coordinate system. Okay, eventually you expect the formulae to simplify, and indeed you get a much simpler formula for the second asymptotic coefficient in this special case. So you see, now everything is expressed through the geometric objects encoded in the principal symbol. So again, there was no geometry when I stated the problem. It's just sitting there in the case when dimension is 3 and you are looking at two equations. Now, there is no integration in momentum. It's all been done explicitly here. So nice formula. So this will be a separate paper that we will submit. Now, I'm not particularly, optimistic about the chances of it, being published quickly, because once you say teleparallelism, you get into trouble. The history of the subject is that Einstein and Cartan promoted this idea in the late 1920s, and they wanted to construct a unified field theory along the lines of teleparallelism, connection with zero curvature, non-zero torsion. Unfortunately, fortunately, at some point Dirac came up with his equation. Everybody forgot about teleparallelism, which was pretty hot at the time. It was like string theory now. Everybody expecting any day great result. So everybody forgot about teleparallelism, and basically Einstein ruined his research career. Nobody took him seriously after that. So I noticed that there are many referees who know the history of theoretical physics. Once you submit a paper which mentions teleparallelism, you immediately get a rejection. In this case, I'm trying to defend myself, say, I'm doing pure maths. I just try to calculate the second asymptotic coefficient of the counting function. And I noticed that in order to do it in dimension 3 for two equations, I need the concept of a teleparallel connection. It's not my fault. It's just the formula that comes out. But still, I'm not particularly optimistic.
Do you need teleportation?
Pardon? Teleportation, I don't deal with teleportation. Okay, now we can have some more fun with this stuff. So let us consider a strange problem: a single neutrino living in a compact three-dimensional universe. Now, maybe for a physicist it's not a particularly interesting problem, but for a mathematician, it's a sort of good test problem. A single neutrino living in a compact three-dimensional universe, and I want to find the energy levels. So to do this, I have to write down something called the massless Dirac operator. It's difficult, you have to study a lot of differential geometry, spinors, covariant derivatives, and horrible stuff. So suppose I write down this eigenvalue problem, and this is all in curved space, of course. And I'm a spectral theorist who doesn't want to learn differential geometry, who just wants to understand, is this the massless Dirac operator or not? First of all, there is a technical difficulty that when you write the massless Dirac operator, you are working with a spinor, a Weyl spinor. The components of a Weyl spinor do not change under changes of local coordinates. But spectral theorists prefer to work with something called the half density, which transforms in a certain way under changes of local coordinates. This is a minor problem. You can just multiply everything by the appropriate power of determinant of the metric. So you can think as a spectral theorist in terms of half densities if you wish. There is no problem here. But still, how do you determine whether your operator is a massless Dirac operator without studying differential geometry? And here is a theorem which we have in a separate paper now. An operator is a massless Dirac operator if and only if two conditions are fulfilled. The subprinciple symbol is proportional to the identity matrix, and the second asymptotic coefficient of the spectral function is 0. So this is a complete description of a massless Dirac operator. So what am I saying is that you don't need to learn really differential geometry if you want to understand Spinner's massless Dirac operator. You can learn spectral theory instead, and this condition, second asymptotic coefficient of the spectral function, is 0. It encompasses all the theory of spinors. Now, is it really an effective way of learning differential geometry? Probably not very effective. You see, first you have to spend like several years learning microlocal analysis, then 30 years correcting all the mistakes in the subject. So it's a pretty painful way of learning differential geometry. But all differential okay, not all, but basic differential geometry of spinors is contained as this condition. Second asymptotic coefficient of the spectral function is 0. Now, you can have some more fun here if you think not in terms of the massless Dirac operator, but the massless Dirac action, so the variational functional for the massless Dirac operator. It's often easier to work with the variational functional than with the operator itself. So the way to give a spectral theoretic characterization of the massless Dirac action without learning differential geometry. It's like this. Okay, I'm working on a compact 3 manifold, consider eigenvalue problem like this, 2 by 2 differential operator, trace 3, and so on and so on. Subprinciple symbol is 0. I put in an extra weight function here. I need an extra degree of freedom. And then, okay, suppose I've learned the spectral theory of systems. I've calculated the second asymptotic coefficient. Now I know how to do it. So it's b, not b of x, just the second asymptotic coefficient for the counting function. And then I think, I have a map now for every principal symbol and any weight function. I have a number called the second coefficient of the counting, the second asymptotic coefficient of the counting function. So I'll be studying this map. But I'll be studying it subject to the constraint that the determinant of the principal symbol is fixed, because I already know the geometric meaning of the determinant of the principal symbol. It's metric, it's nothing else. So if I say the determinant of the principal symbol is fixed, means I just exclude gravitational effects. And okay, this separate result, which I hope to publish with my co-authors, that this map is simply a map from a spinor field to the massless Dirac action. And it's done by explicit calculation. There is nothing else here, just careful explicit calculation. So think of it. You have a matrix, 2 by 2 trace-free Hermitian matrix. You know its determinant. I'm well aware of the time. I have 9 minutes, I think. Yeah? Okay, so you know the determinant of this matrix. Can you determine the matrix uniquely? Of course not. The determinant of a matrix does not determine the matrix. You have some additional degrees of freedom. And these degrees of freedom have a name, spinor. Basically, that's why spinors were invented for it. So it's just a matter of doing calculations that you see that the second asymptotic coefficient of the counting function, in the simplest case, 2 by 2, dimension 3, and so on, has the geometric meaning of the massless Dirac action. Shows again why it was so difficult for those analysts, spectral analysts, to get the correct formula for the second asymptotic coefficient. They entered a different subject area, hardcore differential geometry, without realizing that they were there. Now, why am I doing this? Because, okay, I like spectral theory, but I also have some other issues. So I have a list of favorite equations. Everyone has their own list, but here are mine. And all these equations, 4 equations of theoretical physics, have speed of light in them. And I've been thinking, why do all these 4 different equations have the same parameter, speed of light, in them? Fortunately, there is an explanation called theory of relativity. For those who are unfamiliar with the subject, here is a 1-minute exposition of the theory of relativity. So Bode is a geometer. he decided to measure distances in a funny way. So he thought of time as an extra coordinate and decided to measure distances like this, called Minkowski metric. Without this term, it would be just normal way of measuring distance. For some reason, he put a term with a minus. And having decided on measuring distances in such a way, God built the world using only geometric constructions. So he played around with connection, curvature, and so on. But as a result, the c, the speed of light, appears everywhere. Because he is a geometer, he just built everything on the basis of geometry using this metric. But there is an alternative explanation, which I am promoting, that God is actually an analyst. And he created a three-dimensional Euclidean world and wrote some system of nonlinear PDEs, which happens to have a parameter, c, in it. And we do not know this, what the system is, but we see some solutions which we interpret as electromagnetism, gravity, neutrinos, and so on. And the only reason the speed of light appears there because it's just there from the very start in this system of nonlinear PDEs, which nobody knows. So that's why I'm planning just to continue studying systems of PDEs and getting something interesting out of it. Because I see some elementary hope in that I can get the basic geometric constructs of theoretical physics simply by performing microlocal analysis. So something that everybody thought was done 30 years ago was never done. Nobody has looked carefully at systems of PDEs. If you look carefully, you see a lot of serious geometry, and you can continue doing it irrespective of whether you get a unified field theory or not. It's a lot of fun. So I discovered a playground spectral theory of systems of PDEs, and nobody has ever done it properly, though it was announced 30 years ago that it was all done. Now, I feel guilty that I've been invited to this conference as not being a specialist in Anderson localization. So I did two things to fix it. First of all, on the way here, I read Anderson's memoirs. So I hope you'll partially forgive me. But I also I started doing some work which may be related to solid state physics, not in the direct way, but an indirect way. I started thinking about something called spectral asymmetry. Now, what is spectral asymmetry? When you study, say, the massless Dirac operator in dimension 3 on some manifold, there is no a priori reason for the spectrum to be symmetric, positive and negative spectrum to be symmetric about, multiplication by -1. And this is so there is no a priori reason for particles and antiparticles to be sort of the same. This was noticed this is curved space, with the metric. So the gravity can in principle break sort of the symmetry between particle and antiparticle. And at the mathematical level, this was noticed by Sir Michael Atiyah, and there is a series of 4 classical papers published in the 70s on the subject of spectral asymmetry. I do not understand these papers, they're too difficult, but what I understand that this is a sensible subject and that they cannot come up with any examples. So the examples that naturally come up are torus and sphere, and there the spectrum is symmetric, about 0. There is no difference between particle and antiparticle. So we try to give an explicit example of spectral asymmetry. So it's joint work with Michael Levitian and with Rob Downs, my PhD student. So we took a torus. So the simplest case is, of course, a torus. And on a torus, you initially have a Euclidean metric, and then you perturb it and see what happens. So here is some sort of connection with solid state physics. We end up with a periodic problem, because torus is a periodic thing. We end up with something similar to what you get in solid state physics, only we are working with the Dirac equation, massless Dirac, rather than with the Schrödinger. And we don't have a potential, we have a metric. The metric is our periodic thing. And I think we found a metric, explicit metric, which breaks the symmetry. We were mostly interested in the 0 eigenvalue. If we can show that we've shifted the 0 eigenvalue, then we're done. We have an example of spectral asymmetry. So what's interesting about this example? First of all, the metric is explicit, pretty simple. It contains a small parameter epsilon. Now, the shift of the zero eigenvalue is very small. It's proportional to epsilon to the fourth for some reason. And by the way, here you cannot apply normal perturbation techniques. The reason being that in dimension 3, the massless Dirac operator commutes with the operator of charge conjugation. As a result, all eigenvalues have even multiplicity. You cannot break them up. You can break them only if you impose a magnetic field, then it will break them up. But with only gravity, you cannot break them up. With non-simple eigenvalues, you cannot use normal sort of spectral perturbation methods. But the really amazing thing about this example, it seems that this is an explicit formula for the eigenvalue. Now, we are looking at a system of ordinary differential equations whose coefficients are trigonometric polynomials. Normally, you do not expect to be able to solve such a problem explicitly. Your solution will not be a trigonometric polynomial. For some reason, it is a trigonometric polynomial. For some reason, for this metric, it seems we get some sort of integrability. I was just wondering whether people working in solid-state physics have encountered such a bizarre situation. You have, a periodic problem. You do not expect to be able to solve it explicitly, but for some reason you solve it explicitly for a particular, some sort of internal integrability. Okay, that's all the contribution I can make to solid-state physics, today. So thanks for your attention.
First, you are 1 minute ahead of your schedule, and secondly, thank you for very entertaining presentation. For those who think that mathematics is a boring subject.
We cannot hear you.
Sorry?
We cannot hear you.
It's not important.
But I want to use this opportunity to apologize to our chairman. I'm sorry I didn't recognize you when I came to this conference, but you took me on a tour of Trinity College a couple of years ago. It suddenly struck me, so thank you for that tour.
Questions?
What did you say before?
It's not for you. Yeah.
So, as the story unraveled, you added more and more terms to the second symptotics, explaining that the previous missed them.
There are three terms in the
How
second.
do we know that this is final answer?
Okay, that's a question that's always being asked. That's a very good question. So we tested in two ways. Unitary invariance. So you multiply your operator on left and right by a unitary matrix function. And the second term, the spectrum doesn't change, the spectral function doesn't change. So the second asymptotic coefficient shouldn't change. Safarov's formula failed this test. Our formula passes this test. In our paper that will appear in Journal of Spectral Theory, we have a separate section, unitary invariance. That's one test. And a second test is for the massless Dirac operator, our formula gives second coefficient 0. In all sorts of important equations of mathematical physics like Maxwell and so on, you expect to get the second coefficient 0 because there are so many hidden symmetries inside you. So we got 0. And that's the second test, and that's where it actually started. I asked my PhD student, put in, use Safarov's formula to check that the second coefficient is 0. And they kept coming back for a year saying, no, it's not.
Just a comment. There have, of course, in the physics literature been many attempts to compute this second term for systems of equations. So in the case of neutrino billiards, this was done by Michael Berry and Raoul Mondragon, who also got 0.
Okay.
Does one infer that was the correct approach?
Okay, thanks. If you could give me the reference, it would be good. I wasn't aware of this publication, but all I can say, I have an if and only if theorem. It's a massless Dirac if and only if the second asymptotic coefficient of the spectral function is 0. So I have a slightly stronger result. But thanks for pointing this.
A separate strand, there was work of Robert Littlejohn on general systems of equations computing the second term, and he had a formula. Now, is that For
I also had formula. You know, I spent a few months checking my old papers. I was glad to know that I managed to avoid all the incorrect publication, incorrect formula, because I always specified that I was dealing with an even order differential system. I'll check out those papers if you give me a reference. But you see, it's a first order system. That's where the massive difficulty is. If you square it, you get a second order, and then these things cancel out. I don't know whether little John studied first order or second order.
I don't remember now.
So Dima, do I understand correctly that in this, for this operator, you can compute explicitly not just eigenvalues close to zero, but all of them?
Yes, yes, yes. But it needs to be checked. We didn't have the time. Basically, it was pointed out by a retired member of staff in our department who specializes in teaching mathematics. He helped us, you know, write this computer algebra problem, and then said, you know, guys, you are increasing the size of the matrix. We use the Rayleigh-Ritz method, you know, 10 by 10, 20 by 20, 100 by 100. You always get the same eigenvalue. It can mean only that you have an explicit solution. John Haidt, you know, pointed it to us. But we need to check it.
Thank you.